Okay. All right, let me roll my sleeves up. All right. Yeah, let's all take a quick breath. Homework's in. No homework due for a while. Midterm soon. But kind of late though, right?
Yeah.
Comparatively to other classes, I think you'll be pretty good in terms of crunch.
When was it?
I have my first
Wednesday
midterm
after
next week.
it's due?
Yeah.
The week
Yeah.
It's so I'll issue it.
No.
The takeaway, not just me.
So I'll issue it on the 20th,
Okay.
and it'll be due back the 27th.
Okay.
So that's during fall break.
Can we email you during the fall break?
Of course you can. Yeah. Now I'm gonna be home, except for that Tuesday. I have to give a talk at Connecticut College, so I will be at College on Tuesday. But other than that, I think I'm home. So, and I mean, even when I'm on vacation, I answer work emails. So of course I'll be there. Yeah. I mean, I keep my work emails on my phone, so it yells at me all the time. So, and I'm the kind of person who gets anxious if I don't respond to emails. So, I have to respond during vacation, otherwise I'll just spend my vacation being anxious about it.
I used to do that, then I deleted the emails from my phone.
What's that?
I used to do that, and then I deleted the work account from my phone.
Yeah, I probably should do that for my own mental health, but I don't. Because if I don't do that, then I'm just going to go on my computer every hour and look at them. So. All right, new topic.
Then you get your steps in.
So we kind of finished enthalpy. And I didn't really go into that much depth about enthalpy, but we'll come back to it in a little bit. What I want to start today is the idea of entropy. And it's going to take us a couple lectures to kind of get through the idea of entropy, but what I want to start with today, right, we're going to get to the second law today, but I want to do a motivational kind of idea to kind of motivate why entropy is such a useful concept. So what I want to look at is what we call a thermodynamic process, or a loop, where we're going to have a system initially in state A, then do something else, where A is going to be at some pressure and volume. We'll call it PA and BA. And then do something else that ultimately loops back to point A. Right? So we're going to kind of like compress the gas, expand the gas, do something to it, and then return back to the beginning. So here's a good idea, a nice drawing of that. I'm going to draw on my pressure volume diagram. Let's say, for instance, here's A. We'll go to some point B. Let's just think about going from A to B. And then what I also want to consider, let me draw it with a different color, is let's go from, then do something else that ultimately goes to B. All right, we'll do a loop here. But you can imagine we could do a loop. Just a second. But you could maybe, for instance, instead of going this way from A to B, we could go like this instead, from in between point C. Right? Do it in 2 steps. So let me draw this a little better. It's useful that I get this correct for this calculation. So let's do, this is point B. Let me bring this down a little further. Like this instead. So here's point C and point B. Okay, so the idea is we want to go from A, we start in A and we end in B. This is our end point and this is our beginning. Of course, there's many different ways to do it. We could just do it this way through along this curve AB, but we could also go to A to C, then C to D, then D to B. And so let's identify each of these steps as one of our pathways that we've talked about, right? We have isothermal, isobaric, isochoric. So let's look at from A to B. The idea here is that this is a proportional to P equals nRT over V. Right? And this is an isothermal path, so we could move from A to B isothermally. Or we could go along A, C, D, B. Right? A to C, V doesn't change, right? So this is isochoric. C to D is isobaric, right? The pressure doesn't change. And this is also an isochoric step from B to C, right? Volume's not changing. So there's two different ways to make this path from A to B. And you can also imagine, this is what I meant by a loop, we could just go around in a circle like this as well. Right? We'll come back to that idea in a little bit. And the question now that I want to ask is how much work and how much heat evolves along each of the paths? All right, so what is delta work and delta Q for path AB and path, we do it with the right colors, A, C, D, B. Are they any different? So let's work it out. Let's do the easy one first, the isothermal path. So AB, path AB, is isothermal. And then let's ask the question, what's delta U, delta Q, and delta W? Well, isothermal paths, no energy change. Internal energy, let's just remember that. U is only dependent on temperature. So U is 0. And then Q and work are equal and opposite to each other, and we came up with an equation. This is an ideal gas. nRT, ln. Let's call these different volumes. Let's call this one VB, PB, VA, PA. So it's nRT ln the volume ratio from initial to final. So that's going to be, or final to initial, so that's going to be VB over VA. Right. And likewise, because delta U is 0, then that means work is just the opposite, or heat's the opposite, right? So all right, so we're expanding the gas, right? The volume is increasing. So work is positive. That means that the system does work to the surroundings and is naturally going to emit, so work is being done by the gas against the piston. So that's positive towards us. We gain energy. And we're losing heat, right? So the system's going to absorb heat and expand the gas. Right, so this means work done to environment, positive in this case, and this is heat absorbed by gas. All right, so we've done everything we need to do for A to B. Right? That's how much work and how much heat is being done. So now let's do the next path. So let's just break it down one by one. So let's look at path A to C first, which is isochoric. And let's write the same thing, delta U, delta Q, and delta work. Well, isochoric means no volume change, so what's the change in work? 0. No volume, no PV work's being done. And the amount of heat that's being released, let's recall that these are at different temperatures as well. This is at VA, PA, TA. This is isothermal, so this is at TB. But C and D might have different temperatures. So this is going to be the heat capacity times the change in temperature, Tc minus Ta. Right, and the net change of work is just the heat. Right, so it's dV Tc minus Ta. Okay. Now let's do C to D. This is isobaric, so there's going to be heat evolution there's going to be heat evolution and work evolution. So the amount of work that's being done is nRT ln V2 over V1. And the amount of heat that's being released is between these two temperatures. So that's going to be Cp Td minus Tc. And the work, the sum is just Q plus W here. Okay. And now let's do path B to D. Again, this is isochoric, so there's no work being done. There's just heat. Sorry, dU and dQ. All right, and that's CV Td minus Tb. And delta U is Q plus W. So the amount of work being done in the isothermal path is nRT ln VB over VA. Now, what's the total work being done? VB over VA, sorry. So what's the total amount of work done for this whole path from A to D? Well, there's 0 work being done in the first step, 0 work being done in the last step, and there's nRT being done, nRT ln VB over VA being done in the isobaric step. So the work for AB is the same as the work for ACDB. Right? So that's nice. Means we do the same amount of work no matter which path we take, but what about the heat? So QAB, what's QAB? Well, it's minus nRT ln VB over VA. And what's the heat in total here? Well, it's the sum of these CV terms. Which is CV Tc minus Ta plus CV Td minus Tb plus CV Td minus Tb. So let's see how that math works out. It doesn't really matter how the math works out because let's see, we have CVTC, CVTD, 2CVTD. And then we have some minus signs here, CVTA minus CVTB minus CVTB, which is CVTC plus 2CVTD minus CVTA minus 2CVTB. Note that the heat being released along step AB is not the same as ABCD, or sorry, ACBD. Right? The heat being released through the isothermal step is just a volume ratio, right, times the temperature. But notice that when we take an opposite path, again, work is a state function for the system. So the work works out the same in both cases, but the heat ends up being completely different. Right? The heat is not a state function in this case. Right? The heat being released by the system depends on the path that you take. It's not. Right? That's an issue. Right? can't really do any analysis on the heat of this process because it depends on the path that we take, right? We have to fix our path completely. And if we're in a situation where we don't know what's going on, what the path actually is, then we're never going to be able to track heat. Heat can imagine if the path from A to B is random. We always know that the work's going to work out the same no matter what random path you take, but the heat's going to be different no matter what path, depending on the path that you take. So that's a problem. So we have to come up with something clever that allows us to express the heat as a path function. Now I'm going to simplify this path just a little bit to make the math a little easier, and it will show the same point. So let me go ahead and erase work over here. I'm going to go ahead and erase this. So what I'm going to do is I'm going to change this path very slightly. So again, we have A to B. And then I'm going to add a second path like this, C, and then increase it like this. Okay? So this is an isothermal expansion. This is an isochoric heating here between B and C, and then the path from A to C is adiabatic. All right, let's do the same analysis again. So I'm going to do it slightly differently. I'm going to tabulate. A, B, and C. The path A, sorry, let me make sure that I understand. So this, I'm going to rewrite this so this is path A, this is path C, and this is path B. So we know A is U. A is isothermal, so delta U is 0 for that. The work being done is, depending on which direction you want to do it, nRT ln VB over VA, and the heat, of course, is nRT ln VB over VA. Okay, so now let's do path B. Path B, the amount of work done is the heat, the volume times the change in the temperature. And of course, there's no heat being involved in an adiabatic process. I'm going to try to. All right, so the total amount of work is just the change in work for B. And then for C, C is isochoric, so there's no work being done. And we're left with CV T1 minus T2. Sorry, let me make sure I have this. This is T1, and this is at T2. Okay, so now, if we look at the path A, work being done is nRT ln VB over V1. So the amount net work, the net amount energy change is 0. And if we look here, if we sum everything up, the net energy change going across B and C to get to the final point also comes out to 0. These are equal and opposite to each other. Right? So delta U for path A is 0, which is equal to delta B C. U. Delta U for BC. Right? So the net energy change is 0, which is what we want, right? Energy has to be conserved, so we're all good there. But now let's look again at the heat being evolved. The heat being evolved in work A and Q, the Q in path A is nRT ln VB over VA. But here we have a completely different term. The net of evolution is this, CV T1 minus T2. Right? So again, Q for A is not equal to the Q for BC. So heat's not a state function. So now what I want to do is something slightly different. We have to come up with a new function for heat that gives us the that gives us the same result no matter which path we take. And so I'm gonna try something new here. So what I'm gonna do is I'm gonna rewrite Q. Let me make sure I have this right. I'm going to take Q and I'm going to divide it by temperature. So instead of tracking Q, I'm going to track Q over T. Why is this not working? Okay, so now what I'm going to do is now add a new column here, delta Q over T. All right, this one's easy. It's just minus N. We just take out the T, and we get ln VB over VA. Step B is adiabatic. It has no heat. Isochoric. Wait a second. Hold on a second. I have something wonky here in my notes. I apologize. Right. Why is this not working? All right, I'm missing a part of a step here. And let me think about where I'm going wrong here. So heat being released from isochoric. So for an isochoric expansion, delta U is equal to, there's no work being done, so it's just dq. Now we divide both sides by T. Oh, okay, right. So the change in heat, so for an isochoric expansion, I see what the problem is. The change in heat is equal to the change in total energy, right? There's no work being done in an isochoric process. So now what I'm going to do is divide both sides by T. So if we integrate both sides by T, we can change U so let's think about PV equals nRT. Volume is constant. Think about this. How do you get this number? So you get 1 over V. Right. So what's going to happen? So let's solve for T here. And so if you have PV equals nRT, that means that T is equal to PV over nR. So this is equal to, oh, sorry, let me change this. This is, so the change in heat divided by temperature is equal to the integral of the infinitesimal change in heat divided by T. And so we can plug in T here. So this is dq equals PV nR. What am I doing wrong here?
Are you trying to make P2 or P1?
Yeah, I'm trying to get nR. I'm trying to get you should get nR ln VB over VA here. You should get the same result. And I'm trying to remember how to derive it from this because I forgot to write it in my notes and now I'm completely lost on this. Yeah, just a sec, guys. I'm sorry about this. This is just throwing me off I know I missed something in my notes. It's just embarrassing. Okay, I'm sorry. So let's go back and look at this again. Let's start this over. I'm going to start this fresh. All right, I understand what I'm doing wrong now. So the total change in heat divided by temperature is the integral, the infinitesimal change in heat divided by temperature. Right, and let's use the first law. The first law says that du is equal to dq plus minus PdV, which is work. So that means that dq is equal to du plus PdV. So let's go ahead and put that in. Like that. And this splits into two terms. So this is going to be the integral of du over t plus the integral of PdV over t. Okay. Yeah. So this gives me so the change in energy with respect to the change in temperature is CV dt. So du is equal to CV dt, constant volume. So that becomes that over t. And then we replace p here with, remember that p is nRT over v.
Yeah.
Right? And so that means that this is the integral of nR dv over v from point A to point B, or rather from T1 to T2. NCV of dt over t. Right, and then so we can integrate this. This is CV ln T2 over T1 plus NR ln V2 over V1. Still doesn't make any sense. Bless you.
Do you deal with pressure? Do you have to plug in?
Pressure. I don't think I need to worry about pressure here. Well, let's do this analysis. So let's look at B. B, the work change is going to be CV ln T2 over T1 plus NR ln V2 over V1. Right. Okay. And then on step C, we're going from T2 to T1, so it's CV ln T1 over T2 plus 0, because V2 and V1 are the same, right? Because it's isochoric. So that's 0. Right, this works out. We call this VB over VA, sorry. Now this term right here is minus CV ln T2 over T1. It's the opposite because right, if you flip a ratio in a logarithm, you get a minus 1 out because you're taking the minus 1 power. So these are equal and opposite. So when you add these up, these go away. And so what you're left with now is that the total delta Q over T for one way is in our do I have a sign problem here? V2 over V1. VA, VB over VA. Oh, okay, I know the problem. The problem is I have the signs wrong here because I have a minus here. So this is a minus and this is a plus, so this is a plus. And this is also a plus. Okay, that was my problem, the sign problem. So notice now that the delta Q over T, now we're in the right step. So that the total delta Q for BC, these two steps, I apologize. The CV terms cancel out and we're just left with NR then VB over VA. Over T, sorry, this is over T. And then for path A, isothermal path, our heat is the same. All right, I'm sorry about that. We're all good now. So what that means now is that delta Q is not a state function. But delta Q over T is a state function. So by normalizing our heat change as a function of temperature, how much heat is being exchanged per unit temperature, everything started magically working together after a little bit of algebra and a little bit of thought. Right? If we just look at delta Q, we have completely different results. But if we go to delta T, we have to change again our integrated function slightly, because when we integrate, we have to integrate with a factor of 1 over T inside the integral. And that allows us to get a measure of heat per unit temperature that's the same no matter which path you take. Right, so the take-home point is that if we divide the change in heat by temperature of the system, then we're guaranteed to always have a state function for heat. All right, we'll see this more. But all we've done is just do a very simple division problem when we've converted a complicated measurement of heat that requires us to think about a path, and we've removed that and made it a nice simple state function by just dividing by T. Okay, so I know that math was a little bit of a pain, I apologize. Well, rather, I'd like to now talk about this idea of what is delta Q over T? What is this? Right, so the units of delta Q over T, of course, are the units are joules per Kelvin, maybe per mole. Right, so it's some measure of how much energy is stored within something at a unit temperature, right? Some given temperature, right? Means that the heat, if you increase the temperature, then that must mean the heat increases by this amount of much per unit temperature, right? And so it's a question about what is that, right? What is this that we're measuring, this kind of temperature-dependent heat content? And it leads us directly into the second law. Because the second law explains exactly what this is. Now, for this class, I really want to kind of talk about a couple different ways to approach the second law. All right? And we're going to look at the second law from three different perspectives. We're going to look at it from a thermodynamic perspective, this idea of delta Q over T. We're going to look at it from a mechanical perspective, the idea of having a box of gas, right? The physical interpretation of it. And I also want to talk about the statistics, the probability of this idea of delta Q over T. But the second law tells us exactly what this number is. And so what I'm going to give you is what's called Clausius's inequality. This is our first definition. for the second law that helps us to define what delta Q over T is. And Clausius says that the change in entropy for a system, which we write delta S, S for entropy, why is S, I have no idea, is greater than or equal to the following inequality. Delta S is always greater than or equal to the total amount of heat exchanged in a system reversibly divided by T. All right, so there's some measurement of entropy, right? This idea of entropy. Some sort of energy that has units of energy per temperature, right? Some sort of energy that is stored within this system. And when we change the energy by moving heat in and out of the system, the entropy of the system, which has units of energy per temperature, unit temperature, has to be greater than or equal to the amount of heat being generated or heat being transferred. The total, right? So this is a sum. This is a small step at a given temperature. So we're summing over all the steps. So along a process, a reversible process, you're going to exchange some heat, and the entropy of the system has to be greater than or equal to that value. Okay? Again, we haven't really defined what entropy is here. But this ends up being a very, very, very powerful tool. Still have not defined what entropy really is, but we know that it's measured somehow by the heat that's being exchanged by a system per unit temperature, right? Something to do with this state function, reversibly. And in fact, what you can show, if a process is perfectly reversible, delta S is equal to delta Q rev over T. But if it's not perfectly reversible, which means like in real life, it's always greater than this value, right? That the entropy change, let me mute my phone, sorry, of the system is always greater than this, something to do with this, again, some unit thermal measure of heat, right? Some greater thing. What this means is in an imperfect system, right, where the system's not being progressed in a reversible way, the measurement you make of delta S, right, we're going to measure this heat coming off the system, will always be greater than the actual heat change of the system. There's always some extra energy that comes out. All right, so imagine delta S is the thing that we measure. We have a box that measures entropy, so called. And we want to go measure a process and measure how much heat comes out of it. And if the system's not perfectly reversible, all right, which all real systems are, we're always going to end up reading out more heat than the process actually requires. It's just strange. What this means is that in any real process, some heat, some extra residual heat, is always released to the outside environment. What this means is that in a real system, imagine that you know that the system has to exchange this much heat to go through theoretically, right? You say, okay, the system requires an exchange, in order to go for completion, requires this much heat per unit temperature to be completed. And when you go measure it, you realize that you end up reading that more heat was released. The temperature of your bath, if you will, or your thermometer goes up more than you would expect. There's some extra heat, residual heat being released by the system, right? Or rather, the system requires you to put more energy into it than you would expect. As if there is an extra tax, right? There's an extra tax of energy that you would not expect the system to have if everything were perfect. Okay? There's always a little bit of extra energy. That kind of comes to what the second determination of our second definition of the second law of thermodynamics. Which says that the entropy of the universe, which is everything outside of your system, is always increasing. What this means is that in order for a system, basically the idea is that in order for a process to occur, for a real process to occur, the universe must always, let me change my wording there. The system must always pay an additional energy tax to Mother Nature. Yeah, right, this is it. So in order for a real process to occur, which is one that's not perfect, one that's not perfectly reversible, right? Or you're not doing an infinitesimal change of your system, your normal system. In order for that process to occur, the universe, everything else accepts, it requests and requires the system to put out an additional amount of heat as a tax for its inefficiencies, if you will. Right? The fact that the system is inefficient means that the system will release additional heat to the surroundings as what we call entropy, right? This idea of a tax. Let's explore this a little bit. Let's imagine that we have a box. Yeah, so the idea is, again, I'm just going to reiterate. I like this note that I have in my notes here. It says that this statement implies that any feasible process and not only a feasible process, but a spontaneous process, one that goes to completion without any additional energy put in, right? You set up the system, you want it to go to a final, you set it up to go to a final step, and the system just evolves into that step, which is what I mean by spontaneous. You don't have to put any additional energy into it. A feasible spontaneous process will always lead to a leakage of excess heat into the outside environment. No matter what you do. And in fact, the third law will show that it's impossible to have a perfect process. Right? That's what the third law will guarantee us, that every process that is feasible in real life is not perfectly reversible. And so any of these processes that is set up to go to completion, right, and I'll give you an example of a spontaneous process in just a second, will always lead to some excess heat being released. Right? There's always some excess energy that's consumed that you lose and you can't do anything with. As this tax that Mother Nature takes from you. So let's look at what I mean by a spontaneous process. So what I'm going to do is I'm going to draw a box here and I'm going to divide it with a wall. And I'm going to seal the box so that it can't exchange anything with the outside environment. So this means no heat or matter exchange outside of the box. And this line, I'll write it in a different color, means only heat exchange. And I'm going to set the box up so that the left box is at TAVA and the right box is at TBVB. Let's do a little bit of energy analysis on this system. So let's see, the volumes are fixed, right? So VA plus VB is a constant. Right, we might be able to move the box, right, with the wall a little bit and change VA and VB, but the sum is always constant. And because the system's isolated, it's not exchanging energy with the outside environment, so the total energy between the sum of the energies of the box is constant. And of course, then this would mean then that the entropies of the box is constant. All right, and again, remember this is the heat of the box divided by the temperature, the heat contained in the box divided by the temperature of the box, by TA plus at TB. Right, two different temperatures. So what this means then is that by the first law, the change in the energy of either box is equal to the change in the heat of the boxes plus the change in the work in both boxes. But nothing's going on in terms of the volumes. The volumes are fixed. So this is 0. And so what we can write this now is that the change in energy for either box, sub-box, is equal to the change in the heat, which is equal to T times the change, whether in energy, times the change in the entropy of the box. Right? If S is equal to Q over T, then Q is equal to T times S. Right? This is always a good thing to remember. dQ is equal to TdS. So let's look at what TdS is. So ds is equal to the change in the entropy of the box of A times the change in the entropy in the box of B. Which is going to be, once we do a little bit of math, is the change in the energy. Let me rewrite this a little bit more. Let me write this on the next line. So ds is equal to the change in total entropy is the change in the entropy of box A plus the change in the entropy of the box B, which is the change in the energy of box A at temperature TA plus the change in the box energy at temperature TV, about TV. And because they're constant, we can write this instead as that ds is either equal to the change in the total energy of the box B times the temperature difference, 1 over the temperature difference, which is the same as the change in the energy of box A times the temperature difference, but reversed. Right, the idea is that if B gains energy, then A loses it, right? So they're equal and opposite to each other. So how does entropy flow depending on the change in temperatures? So what is ds less than 0 if TB is less than TA, or TB is less than TA. Remember, entropy has to be increasing. So if TB is greater than TA, this is a smaller number than this number. Right? So let me write that down. If TB is less than TA, or sorry, TB greater than TA, then for ds to be greater than 0, this is negative, so this has to be negative. So the amount of energy for the system to equilibrate, B has to lose energy. Now if TA is greater than TB, for ds, for the entropy change to be greater than 0, then the energy of box B must increase. Well, this should make sense. If box B is warmer than A, how would you imagine? Let's think about it this way. If this is the outdoors, and this is your dorm room, or your apartment, your bedroom, okay? And let's say the outdoor temperature is warmer than your dorm room. Which way does the heat flow? Yeah, warm to cold. Right? If outdoor, warmer. Likewise, if your dorm room is warmer, then it flows out to the outside. Right? And that's exactly what this says. In order for this thing to equilibrate, right? And remember, the entropy always has to be increasing. Right? So ds has to be greater than 0 for your equilibration. That would mean that if the B box is warmer than that, then the B box has to lose energy because it's transferring its heat to box A. Likewise, if the box A is warmer than B, in order for the system to go to completion, B has to gain energy, right? Hot has to go to cold, right? This is just saying that hot heat flows to colder regions. Notice that the only thing that necessitates this requirement is that the second law has to be approved, right? That the entropy has to be increasing. And so one way that I like to think about entropy is the energetic equivalent of the arrow of time. There's a specific direction that energy has to flow to satisfy ds is greater than 0. Right? And that means that the system will always go along that trajectory. Right? And so it enforces that given a system like this, where TA is not equal to TB, where there's some energy can exchange between the two boxes, that there's only one direction that the system can go in. Right? The one that satisfies ds, that satisfies that the entropy change is increasing. Right? So this enforces any system to spontaneously equilibrate, right? To go forward in the way that you would expect it. Enforces that arrow of time. Right? In order for you to reverse that, let's say, for instance, that you have the outdoors are warmer than, the dorm room is warmer than the outdoors, but you want to pull heat out of the outdoors and pump it into your dorm room. Well, the way you do that is you pump energy into the system, right? You have to pay energy to pump additional heat in to go backwards, right? You have to take a heater, do some work to generate additional heat from the outdoor air in order to pump that into your room, to pump it opposite the direction the entropy will flow. Right? And that's the idea. So the idea of spontaneity, a spontaneous process, is one that is completed without any additional energy input. And satisfies delta S is greater than 0. It's interesting. So what entropy is in some ways an enforcement of a particular direction of the way energy flows, right? Energy has to flow in a way that allows, that basically says that the entropy change has to be greater than 0. And you always have to add entropy into the system for the system to go to completion in the direction you expect. Right? So entropy determines the arrow of time, right? If we're given this system and we ask the question, if we just leave the system as is, we don't do anything to it, how does it move? Well, we know that if TA is greater than TB, then heat's going to flow from A to B. It's not going to flow the opposite way. Right? So time is always moving in this direction. Right? The energy is flowing in the same direction as time. And that's what entropy enforces. If, for instance, if a system can be spontaneous, a process can be spontaneous and ds is less than 0, then the opposite thing is going to happen. So it's very interesting that basically the second law basically limits the amount of paths that the system can take, and that it always has to satisfy that the total change in the heat divided by the temperature is greater than 0 for the process. Any questions about that so far? A really good example of entropy is this. On the homework, there's going to be a question. The homework, there's a very similar question to this where, and I'll explain it to you right now. The idea is that you have a similar box, and let's say you have n molecules in this box and 0 molecules in this box. Now what happens when I lift this off? When I remove the wall, what happens? Well, at a long time, some molecules will move away into this region. And so the initial state, I'll write it up here, is n and 0. We remove that, and we're left with n over 2 divided on one half and n over 2 on the other half. Okay, that's what we expect to happen, right? And in fact, this is what entropy tells you has happened. In order for ds to be greater than 0, the only way this system can evolve spontaneously after opening the wall is for half of the molecules on average to move to the other side. Right? This is the process that generates the most, this is the most positive delta S possible. This is the way the system wants to evolve. But what if, for instance, let's let n equals Avogadro's number, 6.10 to the 23rd. Right? So you have a mole of molecules in this box. Okay. And the question that the problem asks is, imagine it takes 1 nanosecond for a particle to switch sides. Okay, so you got some particles here along the edge, right? It takes a nanosecond for them to change back and forth. Okay, right? They're moving around at some speed, and it takes a nanosecond. And the question that I ask is, how long would you have to wait for, let's let this call n left and n right, such that, right, so on average n left is equal to n right, if such that n left minus n right is equal to 10 to the 10. Right, there's 10 to the 10 extra molecules on either side. Right? That seems like a lot, but it's not compared to how many molecules are in there, right? It's 10 to the minus 13 fraction. So this is a 10 to the minus 13 fractional difference from equilibrium. Very small. Right, so the molecules are going to be moving randomly, right? We know that they're ideal gas molecules that are moving in random directions. Right, so you can say, well, since they're moving randomly, there must be some amount of time. Eventually, I'm going to observe the system, and there's going to happen to be more molecules on the left than there are on the right. Just by random luck. Okay, and the question I ask is how long, if it takes a nanosecond for a particle to switch sides, how long do you have to wait until just randomly 10 to the 10 particles are on one side instead of the other one? There's an excess on one. The answer to this question, the time required is on the order of 10 to the 55 seconds, which is longer than the lifetime of the universe. This is why entropy and thermodynamics and thermodynamic equilibrium is so powerful. Is that entropy enforces the system to mix. Right? The entropy forces, right, the system is going to want to evolve in a way that maximizes the entropy. And the way that it does that is if it moves half the particles onto the other side. That's the optimal path. Right? So the system will evolve after everything's diffused and moved around to n over 2 on each side. Right? But we know that they're ideal gas particles. They're going to be bouncing back and forth. Right? You can imagine that maybe the system can randomly come backwards. Even. Right? It turns out that this time is on the order of 10 to the 155 seconds, I think, or something like that. Right? It's an absurd, ridiculous number. And so I asked the question, well, let's do something more reasonable. What if only 10 to the minus 13 fractional difference of molecules are on each side, right? 10 to the 10 difference, right? And that's still longer than the lifetime of the universe, right? So entropy enforces motion in a particular direction, which is to maximally mix everything. And the fact that we're at such large numbers of molecules, or so many molecules, that the system is so random that to see even a tiny, tiny, tiny fractional difference from randomness or from the expectation from entropy would take longer than the lifetime of the universe. Right? So it's basically impossible to ever see any deviation from this path. Right? This is why we always assume that when you have a system like this, right, where you have one area warmer than the other, that heat's going to exchange from warm to cold. Or if you have a region where you have more mass than another one, that mass is going to distribute equally along both sides. The same idea. Right? So entropy enforces that direction. And randomness also enforces it. Right? The randomness of life, which turns out to be related to entropy, right? Entropy determines that a system progresses in a particular direction, and the entropy of a system also precludes you from ever seeing a system out of equilibrium, right, by even a small fractional difference. Right? Once we get to a large number of molecules, right, this is a macroscopic scale set of molecules, that the amount of time required to see it is basically unphysical. Right? So entropy enforces a flow of everything in a particular direction. And it also provides a significant amount of randomness to the system that basically guarantees that the path, the final step that maximizes delta S is the one that happens, right? So the optimal path in a process is one that maximizes delta S. Right, so entropy in some ways is a measure of randomness. Right? Maybe you've heard entropy as a measure of disorder. This doesn't really explain why that is, but entropy wants you to disorder the system as maximally as possible. We go from an arranged state where you have n molecules here, and since there's only an option, right, it's going to the most maximally random state, which is n over 2 on each side, right? So this is organized and this is disorganized. And the system will always evolve spontaneously from an organized state to a disorganized state. A really good example there, you can see the idea of entropy in many different categories, not just thermodynamics. A really interesting example of entropy in kind of a physical sense is that if you take a plate, for instance, and you put a ball of sand in it, right? A little cup of sand. So we have a plate, and then what you do is you go to the beach, pick up some sand, which I'm going to draw in here, right? And you're going to make a nice little pile in the middle of sand here, right? Make all this time to make a nice little pile of sand in the middle of the plate, right? And now what we want to do is we want to evolve the system with a little bit of energy, right? So let's do something to the system. Let's shake it, right? We're doing a process to our system. We have a highly ordered state of sand. And what happens when we shake it? Well, there's possibility that you might shake it enough. Two different kinds of shakes. One might give you the exact same result, but you just shifted it. Right? There's that possibility. Or you might have a more likely possibility, which is that you just distribute the sand in a disordered way across the plate, right? Now, you go do this, you go set this up at home. Do it 20 times, and tell me how many times this happens. I guarantee you it's 0. 20 out of 20 times this is going to happen, right? If you shake it enough, you're going to lead to a disordered state. You're never going to, even though it's feasibly possible for everything to shake in such a way that you just shift the ordered pile to a different part of the plate. I guarantee you do 1,000,000 times, you're never going to get this, right? And that's because the entropy here, the change in entropy, we'll call this SA, this has entropy SA, this has entropy SC, and this is SB. That SB minus SA is greater than SC minus SA. Right? You go from a lower entropy, from going from A to B, you go from a low entropy state to a high entropy state versus going from an entropy state effectively, right? This is effectively 0, right? The ordering of the sandism is exactly the same. It's small. So you're guaranteed that 99% of the time, if this is a random enough shaking process, that you're always going to end up with a disordered system. Right? And the only way for you to go backwards, right now you want to reverse this process. Right? I want to go from B back to A. Well, you could shake it a bunch of times, but I guarantee you that's not going to work. Right? You're just going to shake it up more. It's never going to come back together. What you have to do is apply energy or apply work to rearrange the system manually. Right? You have to take a scoop, use a little bit of energy, and reorder the system yourself. Right? You have to put energy back in to order the system. Right? But if you imagine that shaking is a natural process, right? The shaking is the thing that you do for the sand. Right? So this orderly process of shaking it is always going to lead to a more disordered state. And in order to reverse that, you have to put in your own energy to scoop the sand out and re-put them back in the pile. Right? And that's the way entropy works. Right? That if you're having a process, a natural process for your system, the system will always go from an ordered state to a more disordered state. Always will. And in order to go backwards, you have to end up putting more energy back into the system to do it manually. Right? You have to reorder things. Right? And this works the same way with gas, right? And chemicals and chemistry. Right? The system, when you let it evolve naturally, will always go to a higher disordered state, higher entropy. And in order to get it back again, you need to put in extra energy to do it. Right? So you have to force. You basically, if this increases the entropy by some energy value, then you have to put at least that much energy, if not more, to put it back into the original state. right? Probably more, right? And you have to do it using work. So that's the idea of entropy, right? This idea that randomness always is every spontaneous process has to increase the disorder of the system. Questions about that so far? Okay, well, it's 4:45. I think we're done for now. Sorry about the math problems earlier. What I want to do now, tomorrow we'll come back to this. We'll do some calculations with entropy, see how we measure it in real life. And I want to talk a little bit about probability. What does it, when we look at a box of gas and we change the energy of the system, what happens to the gas itself? Right? We'll talk about how entropy is connected to physical parameters and how the randomness of the gas changes. We'll be able to define that mathematically. And we'll have a really lovely definition for entropy. You too, thank you.
We got a question for you.